Hello, everyone. My name is Luke Montalvo, and I am an undergraduate research assistant at the University of South Alabama in Mobile, Alabama. This is a short summary on some research done on developing in situ permeability and volumetric requirements for open graded friction coarse pavements. If you didn't know, open graded friction coarse pavements, also referred to as OGFC, is a functional mixture used in areas where high intensity of rainfall may lead to flash floods. Minimum volumetric requirements on the OGFC pavement is needed to ensure its functionality of rapid drainage. This study was aimed at developing in situ permeability and interconnected air voids content requirements for an OGFC pavement under various rainfall intensities. The four specific tasks of this research were to quantify the relationship between volumetric properties and hydraulic conductivity, evaluate the ultimate drainage capacity of OGFC specimens using a laboratory-developed rainfall simulator, develop an in situ drainage requirement for a field project based on a case study, and lastly, characterize the quality of drainage of OGFC pavement with respect to drainage time. Figure 1 shows the aggregate gradation of the OGFC mixture. It is also important to note that a number 90 base asphalt modified by TPS additives, which is a thermoplastic rubber, was dosed at 8.1% by weight of total mix. Optimal binder to aggregate ratio was designed as 4.3%. Equation 1 was used to calculate the interconnected air voids. Equation 2 was used to calculate the permeability coefficient. The ultimate drainage capacity is the maximum capacity that allows a complete runoff without clogging or overflow, which is defined as an ultimate drainage capacity, or C sub U, in this study. From a practical standpoint, rainwater flows vertically through the OGFC as well as laterally along the underlying layer until the OGFC layer is saturated. Figure 2A shows the OGFC specimens that were fabricated for this study. It is a 30 by 30 centimeter square with a sealed bottom. Figure 2B shows the rainfall simulator and permeability measuring apparatus that was used to measure the ultimate drainage capacity. Figure 3 is the apparatus for measuring vertical and lateral drainage time. Table 2 summarizes the data that was recorded from using these two apparatuses. Figures 4A and B show the relationship between interconnected air voids and permeability coefficient in milliliters per 15 seconds. Also, figure 4B shows the permeability coefficient in milliliters per 15 seconds versus ultimate drainage capacity. Using these two plots, equations 3 and 4 were formulated. Equation 3 shows permeability coefficient as a function of interconnected air voids. Equation 4 shows the ultimate drainage capacity as a function of permeability coefficient. Continuing, for a field project associated with this study, which was a two-way, 8-lane, the flow path is no longer the laboratory fabricated slab specimen. Considering flow path of 3.75 meters times 4 lanes and replacing ultimate drainage capacity by permeability coefficient, based on equation 4, the in situ ultimate drainage capacity was defined as equation 6. Equation 6 is applicable to the field project that has a 5 centimeter thick OGFC 15 meter flow path and a 2% cross slope. Considering the correlation, interconnected air voids content, and permeability coefficient from equation 3 and the designed air voids content, the critical rainfall intensity is determined as equation 7. Table 3 summarizes the in situ permeability coefficient and interconnected air voids contents requirements. The field project, which was in Xi'an, China, was defined as most major rainfall events were classified as being small and medium intensities. Thus, an 8 millimeter per hour could be used as a rainfall intensity for design, as shown in Table 3. Table 4 shows the in situ permeability coefficients and interconnected air voids contents requirements for multiple lanes. And lastly, Figure 5 shows the drainage time study result. The correlation between drainage time and interconnected air voids content yielded that drainage time is equal to 5.91 minus 0.24 times the interconnected air voids. According to AASHTO 1993 Design Guide, the water should be removed within 2 hours to account for an excellent quality of drainage. It is determined that a minimum interconnected air voids content of 16.3% be needed for an OGFC pavement for this case study project. That is all I have. Thank you very much.